We give it a couple of
Okay,
minutes.
great, sure.
Yeah,
Sure.
I'm also just waiting for the streaming to start. Then we
I
will
think this
start.
live streaming is started. Yeah.
Okay, so yeah, now we are live also.
Where are you guys right now? Are you all in India, or are you all over the place?
I am in India.
Most of
Okay.
us, I think, are in India.
Most of you are in India. Okay.
Yeah, it's a virtual conference. I guess we had to make a call at some point, and I think I had some doubts when things got better in the fall, or whether we should have had. But then I think
yeah, we've all been on this roller coaster, right?
Yeah.
But when did you make the decision to make it all virtual?
Actually, fairly early. In fact, this was happened during the bad wave in India. We had to make some kind of a call, and it felt like it was better to make a call earlier than later. And
yeah, I understand. But by the way, I apologize about the Saturday morning thing. That it turned out that it conflicts with our family plans. I can't do that.
It's perfectly fine.
I thought that even though it was last minute that I'd be able to do it, but it looks like no. Okay.
In answer to your question, Scott, some of us are all over the place.
Yeah, in fact, you didn't
Hi, Eric. How are you?
Thanks, Eric.
Okay. Are you in New Brunswick or thereabouts?
Yes, well, thereabouts, a little bit north of Winton.
Yes, okay.
Yeah, I just came to India just for visiting my parents and also to be in the Indian time zone while this is happening. And
all right, cool.
So I'm in my parents' house.
Oh, all right, cool. Well, wow, your parents have an awesome place, apparently. Right on the beach there. That's pretty amazing.
No, I didn't want to showcase my sort of rudimentary setup here, and I thought I would put in fact, I found a picture of a Goa beach. I was supposed to go to Goa, so
that's Goa. Okay, all right, cool.
Okay, so Scott, if you are ready, I will hand over to Meena to introduce you. And
absolutely.
Yeah. Okay, so Chandra, I think it's okay to start now, right? Yeah. Okay.
Yeah, over to you, Meena. Yeah, please.
Okay. Yeah. So welcome everybody to this session with our invited talk by Scott Aaronson. It's my great pleasure to introduce him to this audience. And of course, I have to start with the cliche that he does not need any introduction, and nonetheless, I will proceed to give it. So Scott is currently a professor at the University of Texas at Austin. And before this, well, he did his bachelor's at Cornell, his PhD at UC Berkeley, and then he spent several years on the faculty at MIT before finally reaching his current place at Austin. His main research interest is focused on quantum computing, on the capabilities and limits of what can be done with quantum computing. He has written this wonderful book, Quantum Computing Since Democritus, converting, I think, the lecture notes from one of his course. So this book is, of course, about quantum computing, but it makes a great tour through ideas in logic and set theory and computability and cryptography and quantum mechanics and what have you. His research has fetched him multiple awards. In particular, the two highest honors that are awarded by the US government on early career scientists, the Waterman Award and the Presidential Early Career Award. He's also won the ACM Prize in Computing. So a stellar career so far and much more to go. He's also, as I think many people in this audience, I'm sure are aware, he's blogger extraordinaire. He has this blog, which is not just about quantum computing, not just theoretical computer science. It's computer science, it's science, it's education, it's policy, politics, it's all of life. And he has periodically these famed Ask Me Anything sessions where really the volume of traffic has to be seen to be believed, because he loves to engage in this kind of debate and conversation. So today we really look forward to having Scott tell us about 28 years since BQP. Scott, over to you.
All right, well, thank you, Meena, for that incredibly kind introduction. I don't know if I'll be able to live up to, but I've I've been to India once for a non-virtual visit when QIP was there in 2008, and it's good to be back, even virtually. Someday I will attend an FSTTCS in person. But for now, I'm very happy to be able to share this with you, in the COVID way that we're all accustomed to now. And I thought about what to talk about, and I could give a talk about kind of the trendiest issues in quantum computing, the quantum supremacy experiments, and the quest to get useful applications, or error correction out of near-term quantum computers. This talk is not going to be about any of those trendy current things. It's going to be about oracle separations involving quantum complexity classes. Okay, and more generally, just what can we say about the power of BQP? BQP is a bounded error quantum polynomial time. Okay, it's the quantum generalization of P. The class of all of the decision problems that we can efficiently solve with a quantum computer, basically. And so you could say, a central question for the field for, almost 30 years now has been, what is the power of BQP? And, maybe we don't talk about it that much anymore, just because, it feels like, well, what can be said about this question in general and our present state of knowledge was already said in the 1990s, and maybe what is there to say about it that's new? So I want to show you that actually we can say stuff that's new. There was a breakthrough a few years ago by Raz and Tal, oracle separation between BQP and the polynomial hierarchy. So basically, I'm going to talk about that, and then I'm going to talk about its implications. Okay, how we were using that as a starting point, how actually, we've been able to say a lot more about the power of BQP, at least in the black box setting. All right, so let me start with just getting everyone on the same page, as it were. Okay, so BQP, bounded error quantum polynomial time. It's a complexity class that was first defined by Bernstein and Vazirani in their seminal paper, Quantum Complexity Theory, from 1993. Okay, and so here are a couple of pictures to orient you in solar system or whatever that we're going to be talking about. So we've got P, NP, the NP hard problems, and so forth, and we don't know exactly where BQP fits in, but what's the sort of most people's guess, or sort of the assumption that most people proceed on, I've indicated with this kind of wavy border, right? Wavy because everything quantum is weird and spooky, right? So we know that BQP contains at least a few problems that are famously not known to be in P, such as the factoring and discrete log problems. Okay, and that was the famous discovery of Peter Shor in 1994 that sort of caused quantum computing to be a field. Okay, rather than just a weird idea that was pursued by a few eccentrics. Okay, we don't know the relationship between BQP and NP, but it is consistent with our current knowledge that they might be incomparable. Okay, so we don't think that we certainly don't know of a polynomial time quantum algorithm to solve the NP complete problems. Conversely, we don't know whether BQP is contained in NP. Okay, so maybe there are problems that a quantum computer can efficiently solve, like simulating quantum systems, for example, but for which a classical computer cannot even efficiently recognize the answer, let alone finding it. Okay, so on the right is a little bit of a more detailed picture. Where BQP is known to fit. We know that it's contained in P space, And in fact, in various smaller complexity classes. So in particular, in our present state of knowledge, there's no hope of proving, let's say, that BPP is different from BQP. Because, if you did that, you would have to prove that P is not equal to P space, which would be a huge deal for reasons having nothing to do with quantum computing, right? So, I've succeeded in sort of one of the canonical activities of a complexity theorist, which is to pass the blame for failure onto somebody else. Okay, as to why we cannot prove today that BPP is different from BQP. Okay, but we do know various things. So Bennett, Bernstein, Broussard, and Vazirani in 1994 showed that BQP to the BQP equals BQP, which means basically that you can give a quantum algorithm as a subroutine, or you could say quantum algorithms are closed under taking subroutines, right? You can always assume the ability to query a problem that's in BQP, and that gives you an overall efficient quantum algorithm. Fortnow and Rogers showed maybe a more surprising result, that PP to the BQP equals PP. Okay, so once you're up at PP, then BQP doesn't make you more powerful. Now, later on, I proved a characterization that PP is the same thing as BQP with post-selection. Okay, and this result of Fortnow and Rogers would be an immediate implication of that. Okay, but so these are various facts. Okay, but now there are, as I mentioned, profound questions that have remained open, all the way from the early 1990s to the present. Okay, and so the ones that I think of as maybe the three most central questions of quantum complexity theory, right, would be, well, first of all, what, if anything, can quantum computers do efficiently that classical computers cannot, right? So is BPP equal to BQP, or like what separates these two classes, or under what assumptions are the two classes separated? Okay, second question, the power of BQP, the one very specific thing we'd like to know is, can they solve NP-complete problems in polynomial time? And if no, then what is the evidence against? Okay, like, if NP is in BQP, does that mean that something else happens that's crazy? Okay, so let's say that's question number two. Question number three is, what is an upper bound, or what's the best upper bound on the power of quantum computing? Okay, so we said that BQP is contained in P space. It's even contained in P to the sharp P and in PP. So, basically, once you have the power of counting the number of solutions to a Boolean formula, then you can do what physicists would call the Feynman path integral. Okay, but for a computer scientist, it just means representing an amplitude in a quantum computation as an exponentially large sum of contributions. Okay, so you can then simulate quantum computation that way. But that doesn't answer the question, is BQP contained in the polynomial hierarchy, right? Which has been a famous open problem. We could even hope for more. Could it be contained in AM? Could it be contained in NP? Okay, and one can ask many, many more arcane questions. So here's a nice example that will be very relevant in this talk. 16 years ago, Lance Fortnow, who was blogging about these things even before I was, raised the question on his blog of, is NP to the BQP contained in BQP to the NP, right? So this is maybe one of the sorts of questions that it takes a Lance Fortnow or someone like that to ask. Okay, but once it's asked, then it's just sitting there as a question, right? Can you, let's say, I want to combine these two very different resources, non-determinism and quantum computation. Then how does the order of combination matter? Or, does it matter? Okay, can we show that there's in Oracle, that relative to some Oracle that this doesn't happen. Okay, that that stood open for 16 years, and actually, it was very, very hard to solve for reasons that I can explain. So formally, like it seems, very, very hard to say anything about these questions, beyond certain like fairly obvious things. So like, here's a point that I made on my blog, probably in 2007 or so. Okay, I pointed out that, well, if this, so like if we think about like these different questions, like, is NP contained in BQP? Is BQP contained in AM? Well, it's very unlikely that both of those are true, right? Because if both of them are true, well, BQP is closed under complement, right? So if it's contained in AM, then it's also contained in co-AM, right? But then if NP is contained in BQP, and BQP is contained in co-AM, then NP is contained in co-AM, right? Or co-NP is contained in AM, which means that the polynomial hierarchy would collapse. Okay, so, all right, fine. We would like to say something a lot more interesting than that. And now, maybe the starting point for what I want to talk about today is that, for BPP, so for classical randomized algorithms, we actually can answer, all of the sorts of questions that I was talking about. Okay, so, it's not like, these things are hopeless, right? It's like for classical randomized algorithms, we know how to say so many more things. So for example, we know that BPP is contained in the polynomial hierarchy. That's the famous Sipser-Gatch-Laudeman theorem from the early 80s. Okay, so in particular, if P equals NP, then P also equals BPP, right? We know that. Okay, we know that BPP is contained in P/poly, right? P with polynomial size advice. That's Edelman's theorem. Okay, and then, this is often given as like an exercise in complexity theory courses, right? We know that if NP is in BPP, so, if there's a polytime randomized algorithm for NP complete problems, then actually the entire polynomial hierarchy is in BPP as well. And in fact, the hierarchy just collapses to BPP. Okay, so now, we don't know any of the analogous statements for BQP, right, in place of BPP. Okay, so now, I've often, pushed the view, including, in my book, Quantum Computing Since Democritus, which, Mina mentioned, that, quantum computation is just, a sort of, generalization of probabilistic computation. Okay, that the quantum mechanics is a generalization of probability theory, where instead of probabilities, which are non-negative reals, we have these amplitudes, which are complex numbers. Okay, but then we having made that one change, we try to develop things as analogously to classical probability, as we can. Okay, so then you might say, well then what is the difference, right? That all of these structural facts, we can prove them for BPP, but we can't prove them for BQP. Okay, well, the difference, this is something that Lance has also stressed very often, and that I think is can hardly be stressed enough in this subject. It's that with randomized algorithms, there's always a certain trick that you can do that has no obvious analog for quantum algorithms. Okay, and the trick is that you can think about a randomized algorithm as just a deterministic algorithm that receives a random string as an auxiliary input, right? So, it's some M that, gets two inputs, X as well as, the randomness string R, and then, we were interested in its behavior on a random R. Okay, but now we can play all kinds of games, like we can quantify over the R's, right? We can use approximate counting to estimate the fraction of R's that cause M to do something or the other thing. We can change the order of the quantifiers, over R and over various other things. we can hardwire R as an advice string, right? And now, what's the analog of any of that if M is a quantum algorithm, right? With quantum algorithms also involve randomness. Okay, but there the randomness is not there at the beginning of the algorithm, right? In a quantum algorithm, the randomness only appears at the end when you make a measurement, right? And then, we have to convert the amplitudes into probabilities, using the famous Born rule, which says that the probability of some outcome equals the squared absolute value of its amplitude. Okay, but until we measure, until we make the measurement at the end, everything is deterministic, right? So there's no notion of sort of pulling the randomness out of a quantum algorithm or pulling the quantumness out of it, right? It's all just this one sort of blob where then the randomness appears at the end. Okay, so now this difference between quantum algorithms and classical randomized algorithms, has been exploited for many, many purposes in quantum complexity theory. Okay, and as one example, it is kind of the crucial observation that's used in the analysis of these recent quantum supremacy experiments, like the ones that Google and then USDC in China, have reported over the past 2 years. Okay, so the theoretical foundations of these kinds of experiments were laid a decade ago when various people, including Bremner, Jozsa, and Shepard, and me and Alex Arkhipov, noticed that there were sort of very, very rudimentary quantum computations that they don't solve any classically hard decision problem, right? It's not obvious how to get them to do that. But what they do is they sample from certain probability distributions over n-bit strings, where it looks very, very unlikely that there would be a fast classical algorithm to sample from those same distributions, or even to do so approximately. And our arguments for that, all of them kind of rested on this fact that, well, if there was a fast classical randomized algorithm, then we could sort of pull the randomness out of it. We could do things like Stockmeyer approximate counting to say, well, now I want to estimate this one particular probability, probability of one particular string, right? And I can make that so that estimating it is a sharp P complete problem, and yet, using my assumed fast classical sampling algorithm, I could then estimate it in BPP to the NP, which would then mean that P to the sharp P would be simulatable by BPP to the NP, which would mean that the polynomial hierarchy would collapse. Okay, so if we don't think the polynomial hierarchy collapses, then we think that these quantum sampling experiments are hard to simulate with a classical computer, right? That was the basic structure of those arguments. Okay, but now we're interested in let's say the original classes, BPP and BQP, not the sampling problems, but the decision problems, and then things become a lot harder, and it seems like it's too much even to hope for even under some standard complexity assumption, let's say a proof that BQP is even different from BPP at all, let alone being different in all of these specific respects that I talked about. Okay, so now this finally brings me to relativization. Right now, since this is a CS audience, I probably don't have to make this analogy. Maybe it'll even obscure more than it clarifies. Okay, but in each field, there are like each field has certain things that you do in order to make progress when you can't make progress. Right. So for the physicists, they have this perturbation theory, right, where they just instead of solving quantum field theory, they just add in particles one by one and see what happens. And in computer science, we have looking at questions relative to an oracle. Okay. Now, of course, this doesn't always tell us the right answer. If famously, IP equals P space and MIP equals NX were proven, even in the teeth of oracles relative to which those statements are false. Okay, but if we don't even know what happens in the relativized setting, then that is sort of an obvious place to look first, right? That, we can sort of first try to understand the relativized setting, and then that will give us a better understanding of at least like what, for which questions are we going to need non-relativizing techniques, right? So, so it gives us sort of some initial guidance about the questions that we care about. Okay, so now, and this strategy has played a central role in quantum complexity theory since the very beginning of the field. Okay, and in particular, it was part of the sequence of discoveries that led to Shor's factoring algorithm in the first place. Okay, so Bernstein and Vazirani show for the first time that there is some oracle relative to which BPP is different from BQP. Okay, now their oracle was not satisfying. It was called recursive Fourier sampling, and it gave an example of something where like a quantum algorithm can do it in n queries, and a classical algorithm requires n to the log of n queries, right? So it was not a polynomial versus exponential gap, okay? But it was quickly improved by Simon's algorithm. Okay, Simon gave a problem, a black box problem, an oracle problem that is in quantum polynomial time, but that provably requires exponential time, an exponential number of queries to the oracle for any classical randomized algorithm. Okay, and then Simon's algorithm directly inspired Peter Shor, who said, well, the problem being solved by Simon looks kind of like finding the period of a periodic function. Okay, and in fact, for literally that problem of period finding, we can also give such a huge oracle separation between BBP and BQP. Okay, but then we can actually remove the oracle and just, where we can instantiate it by the modular exponentiation function. And when we do that, then we get a fast quantum algorithm for factoring, okay, which no longer requires any oracle. Okay, so you see how oracle results can often, be the source of insight. Or, they can ultimately give us ideas for what to prove in the real world. Shor's algorithm was, one of history's great examples of that. Okay, so now another important thing that we know is from Bennett, Bernstein, Broussard, and Vazirani. And they show that there is an oracle relative to which NP is not contained in BQP. Or in other words, so in particular, they showed that there are black box problems that like searching a list of size n that require that requires square root of n time by any quantum algorithm. Okay, and this was actually discovered before Grover's algorithm. Grover's algorithm can actually search a list, of size n in square root of n time quantumly. Okay, but then after that, this BBBV theorem acquired the interpretation that Grover's algorithm is optimal. So, so even a quantum computer will not get an exponential speed up for just the pure problem of black box search, right? It will only get a square root speed up. Okay, and this is one of the most important facts that we know about quantum computation. It is maybe 80% of like what is sold to investors and the popular press about quantum computation, even to this day, is sort of encourages the image of a world where the BBBV theorem is not true. Okay, and yet the BBBV theorem is true. So this is a big problem that we have with the public understanding of this field. Now oracles were used to discover many other things about BQP. So Fortnow and Rogers showed that there is an oracle that makes P equals BQP, and yet without collapsing the polynomial hierarchy. Okay, so in other words, like if you thought that BQP equals P collapses the polynomial hierarchy, then that can only be for a non-relativizing reason. Li Ji Chen and I, a few years ago, were able to extend that to show that there are even oracles where every distribution that's sampleable in quantum polynomial time is approximately sampleable in classical polynomial time, right? So there is no quantum supremacy, in other words, and yet the polynomial hierarchy is infinite. Okay, so we show basically if you want to prove the central conjecture in the theory of quantum supremacy, that that these sort of approximate collapse of classical and quantum approximate sampling should collapse the polynomial hierarchy, then this also has to be for via a non-relativizing proof. All right. Now, what about upper bounds on BQP? Okay, so Bernstein and Vazirani, implicitly, and then John Watrous explicitly, sort of, established that there are oracles relative to which BQP is not contained in NP. And in fact, one can even get BQP not contained in MA. Okay, but the progress kind of stopped there for almost 20 years. Okay, no one was able to get an oracle relative to which BQP is not in AM. Okay, let alone BQP is not in the polynomial hierarchy. Okay, even though this seemed kind of plausible, and I worked on this problem. Many others worked on it. And they were open problems. So what I did manage to do in 2009 was to propose a candidate problem for separating BQP from the polynomial hierarchy. Okay, and this problem it became known eventually as correlation. Okay, because it involves the correlation between one function and the Fourier transform of a second function. So here's a brief definition of the problem. Okay, we are given black box access to two Boolean functions, let's say f and g, okay, that map 0, 1 to the n to, let's say, 1 and minus 1. Okay, and now we're promised that one of two things is true about f and g. Okay, case one is that they're both just uniformly random and independent of each other. Case two is that f and g are random individually, but they are correlated in a very specific way. Okay, G is very close to F hat, or let's say G is like the rounding, or like a discretization of F hat, the Boolean Fourier transform of F. Okay, so now the question is just to decide which, right? Decide whether there is this large correlation between G and F hat, or whether they're just two completely uncorrelated random functions. Okay, so now what's of interest about this problem is that I showed that in some sense it is a maximally easy problem for quantum computers. Okay, it can be solved using only a single quantum query to both F and G, a single superposition query. Okay, now I conjectured that this problem is not in pH. All constant depth circuits of AND/OR and NOT gates should not be able to tell whether F and G are correlated.
So Scott, I think we missed a few seconds.
Yeah. Okay. So all right. So I was saying you should not be able to tell whether F and G are correlated or uncorrelated if you are an AC0 circuit. That was my conjecture. Okay. And so I couldn't prove it. But it was and I realized that it was going to require some new techniques for AC0 lower bounds, even though we already had a lot of techniques that, they were not powerful enough. And so finally, after working on the problem for 4 years, Ron Raz and Avishai Tal were able to invent the techniques that were needed and finally proved my conjecture that correlation is not in pH with their breakthrough analysis of the Fourier spectra of AC0 circuits. In fact, they proved something stronger than that. They proved that a pH machine, an AC0 circuit, if you like, can only have 1 over exponential and n bias at guessing whether F and G are uniform or correlated. Okay, so and that is a fact that we use actually in the new work, which I want to tell you about right now in the remaining 20 minutes of this talk. Okay, so just a month ago, I guess, I, along with 2 students who I've been working with, William Kretschmer, who's my PhD student, and Devon Ingram, who is a PhD student in math at University of Chicago, who was an undergrad. He was working with me on this. So we put a paper on the archive, which we called The Acrobatics of BQP. Okay, and and basically our starting point was to say, well, once we're in this post-Rosenthal world, where we can actually separate BQP from the polynomial hierarchy by an oracle, then what else can we do, right? Like, which other of these like old open problems about the power of BQP could we now pick off? And we found that actually, there are a bunch more things that we can do, but that, Rosenthal by itself was not enough to do them. Okay, we needed that, but we also needed more. So let me just, in as whatever time I have, tell you a little bit about what we've been able to do. So, all right, so like, here are some easy things that, that I'll just, think of it, just to warm you up. Some easy corollaries of Rosenthal. Like, there is an oracle relative to which BQP is not in NP/poly. There is an oracle where P equals NP, but neither of them's equal to BQP. Okay, let me show you how that one would go. Right, so we can use the correlation problem to make P different from BQP. Right, that's what it does. It's easy for quantum, hard for classical. Okay, but then what we can do is, like, for each positive integer k, we can recursively encode into our oracle the answers to all of the possible queries made by NP machines, that are querying the part of the oracle that we've already constructed, right? And we do that in a staggered fashion, where, like, in order to access the kth part of the oracle, like, you need an n to the k time machine, like, because it involves strings of length n to the k or something, okay? Just to make sure that, like, the queries to earlier parts of the oracle are not querying the answers to that we encode later, right? Which would mean that they could query about their own behavior, and then we would have like a paradox or contradiction. I want to avoid that. Okay, so what we can do in this way is by recursively encoding the answers to the NP queries, we make P equal to NP. But then by the Rosenthal theorem, we can argue that we're still not making P equal to BQP. Okay, basically, because these pH queries that we get are still not able to solve correlation. All right, now here's a more interesting statement. There is an oracle that makes P equal to NP, and that makes BQP equal to P to the sharp P, let's say, but then neither of them are equal to each other. So in other words, we can make, even in a world where P equals NP, we can make BQP kind of ridiculously powerful, okay? Its aspirations are not constrained by NPs, okay? And, I'm not, gonna go through all the details of how you do this, right? But, you make P to the sharp P much stronger than pH, and then what's going on? There's some feedback. Okay, yeah. So okay, so we we do kind of some known oracle construction tricks, and then we appeal to Rosenthal at the end, right? Another thing you can do that way is you can say, let's say you want an oracle where NP is in BQP. Okay, so quantum algorithms are strong, like NP complete problems are easy for them, but it doesn't collapse the polynomial hierarchy. Okay, you can do that as well. So you can say like, if so BQP is very different from BPP in this respect, right? If NP is in BPP, then the polynomial hierarchy collapses, and that's relativizing. That's true for every oracle. Okay, but we can say, there are oracles where NP is in BQP, and yet the polynomial hierarchy does not collapse. Okay, so if anything analogous is true quantumly, then it has to be for non-relativizing reasons. Okay, and once again, this is going to use Rosenthal, and in this case, a very convenient way to do it is to use another recent achievement by Rossmann, Servetio, and Tan, who actually also Hastad was involved in, I think, the journal version of the result, where they achieved an oracle where they showed that relative to a random oracle, the polynomial hierarchy is infinite. Okay, so we can use that, and then we can first make the polynomial hierarchy infinite with our random oracle. Then we can encode all the answers to all the NP queries into correlation instances, and that puts NP into BQP. And then we can use Ras-Tal to say plus a hybrid argument, like similar to this BBBV, to say that, well, okay, but it still looks random to the polynomial hierarchy. Okay, so it doesn't recollapse BH. Okay, but now to go further than that, we needed more than just Ras-Tal, as I mentioned. Okay, so now since the 1980s, a central tool for proving oracle separations, for example, that pH is different from p-space, has been the so-called method of random restrictions. Okay, so you randomly restrict your input. You restrict many of your input bits randomly to either 0 or 1, and then you argue that with high probability, the unrestricted part of your function is still pretty complicated. Okay, but if your function had, let's say, a small circuit, like an AC0 circuit, for example, then that could not have been true, and therefore your function is not an AC0. Okay, that's the random restriction method. 30-second summaries. Okay, so the first thing that we did is that we showed that quantum algorithms also satisfy a random a property of simplifying under random restrictions. Okay, and this is very, very useful to us, and maybe will be useful to other people as well. Okay, so here's a detailed statement of our lemma. The details are not going to be so important, but basically what it says is that if you've got a quantum algorithm, let's say Q, and it makes some number of a small number of queries to in input string X, let's say it makes T queries. Now, if I randomly restrict the inputs, if I randomly restrict like a large fraction of the bits of X, and I look at Q's behavior on the remaining bits, then there might be a few bits that really that remaining part really depends on a lot, and that I would have to query. I call that set L. Okay, but once I condition on that small set L, then the quantum algorithm's acceptance probability is not very sensitive to kind of flipping the remaining bits in the unrestricted part of the oracle. The way that we prove that is once again just this BBBV theorem. The fact that Grover's algorithm is optimal, and basically just combining that with Chernoff bounds and being very careful. Okay, so it's kind of a repackaging already knew about quantum computation, but I think that this is actually an extremely useful repackaging of what we knew. Okay, so here is one example of an application of this. Okay, so every K, there is an oracle relative to, and in fact a random oracle relative to a random oracle, sigma K plus 1. So the K plus first level of the polynomial hierarchy is not contained in BQP to the sigma K. Okay, so in other words, not only does a random oracle make the polynomial hierarchy infinite, but BQP is not going to bridge those gaps. Okay, so it's like Rossmann-Servetio-Tan, but now with quantum, right? And indeed, that's exactly how we prove it. We look carefully at the innards of the Rossmann-Servetio-Tan theorem, the oracle, that a random oracle makes pH infinite. And we show that where they use random restrictions, actually a more general thing that they call random projections, we can combine that with our kind of quantum random restriction, and it all works. Okay, so once we have this notion that random restriction can sort of play well with quantum, then we get this as kind of this kind of falls out very easily. Now, maybe our interesting thing that we prove is that there is an oracle relative to which NP to the BQP is not in BQP to the NP. Okay, and in fact, even stronger than that, NP to the BQP is not in BQP to the PH. Okay, so this resolves Lance Fortnell's problem from 2005. Okay. It was harder than we thought to do this. Okay, but the separating example, if I want a function that's in here but that's not in here, then what should it be, right? And from what I've already told you, right, you could almost guess what the function is going to be. We're going to compose the OR function, an OR of exponentially many inputs, with the correlation function. Okay, and so OR composed with correlation, well, I can do that in here because BQP solves correlation, NP solves OR. Okay, but here it's like the resources are in the wrong order, right? Like, if you've heard, like, there's this very charming story about this person who can't walk, right, and this other person who's blind, right? But the first one, the one who can't walk, gets on the shoulders of the second one, right, and then directs him around, and in that way, by working together, they're able to pick fruit from a tree, right, by compensating for each other's death, right? But imagine that the blind person had gotten on the shoulders of the person who can't walk, right? That would have been pretty useless. Okay, and so so that's what we want to say here, that the quantifiers are in the wrong order. Okay, how do we formalize this? Okay, and there's a very interesting difficulty, which is that, well, suppose okay, so Rosenthal already showed that correlation, is hard for pH, right? So we already know that. Okay, but that's not enough, because suppose that it were suppose that correlation were like a homomorphic encryption scheme. Okay, so like we know that we're if we're encrypting the result against pH, right? pH cannot tell whether a given pair of functions is correlated or uncorrelated. Okay, but imagine that given exponentially many instances of the correlation problem, suppose that in pH we could produce a new correlation instance whose answer was the OR of the answers to the input correlation instances. Okay, so imagine that we could sort of homomorphically compute the OR function in AC0 with correlation as the encryption. Okay, well, that's a very weird possibility, but I mention it because if we could do that, then NP to the BQP would be contained in BQP to the NP, relative to our oracle, right? So that is an example of the sort of bizarre possibility that has to be ruled out. Okay, so so in order to rule that out, what we needed to do was use a concentration theorem for the block sensitivity of AC0 functions. And to get that, we built on a recent paper by Gopalan, Servetio, Tal, and Vigderson, where they were actually trying to prove the sensitivity conjecture. Right? And this was just like a couple years before Hao Huang solved the sensitivity problem using a completely different method, right? And so, they might have, been, they might have, felt sheepish or something that, oh, I guess, our paper is no longer relevant. Well, guess what? Their paper is relevant. Okay, we were able to use what they do. Okay, because one of the things that they do in their paper is that they prove a concentration theorem for the sensitivity of any function in AC0. Okay, and so we were able to extend that to block sensitivity, and so in particular to things like, given all of these functions, see if is there one that is sort of different from the others where otherwise the functions are going to be random, right? So in particular, we're going to use, we're not just using the fact that correlation is in BQP and that it's hard for pH. We are also using the fact that correlation involves distinguishing the uniform distribution from, a non-uniform distribution, or so, from this weird other distribution. Okay, so we're saying that, AC0 functions, when you feed them the uniform distribution, they tend to have very concentrated behavior, right? And you can, they tend to do very predictable things. And if this OR of correlation was in BQP to the NP, then that would have to violate that property of AC0 circuits. That's basically what we do there. Unfortunately, I don't have time to explain more details. Okay, but I will mention that all of these sorts of results are only possible in a post-Rosenthal world. Because, if, for example, BQP were contained in AM, then all of these things that we're trying to prove would be false. Okay, and they would be false via relativizing proofs. So, for example, if BQP is in AM, then, I'll give it as an exercise for you. It's not very hard to show that NP to the BQP would then be contained in BQP to the NP, right? So at the very least, for our oracle to do this, our oracle has to put BQP outside of AM, right? And we didn't even know how to do that before Rosenthal's breakthrough a few years ago. Okay, so, okay. Now, we also, I'm happy to say, we're able to prove the converse direction. Namely, there exists an oracle relative to which BQP to the NP is not in pH to the BQP. Okay, here the separating example is the composition of correlation and OR. Okay, so we go in the reverse direction. I have a whole exponentially many instances of search, of like just computing the OR function. And, when I decode all of them, like I compute the value, what is the OR 0 or 1, then this gives me a correlation instance, which I'm then supposed to solve. Okay, so, clearly this is in BQP to the NP, almost by definition. And we want to show that it's not in pH to the BQP. Okay, and the intuition here is that, well, this BQP oracle is kind of useless to us, okay? Because I've got these exponentially large search problems, and if I'm a BQP machine, then I shouldn't even be able to solve, even one of these, or at any rate, no more than a few of them, right? And so then, like I might as well not even use the BQP oracle. I might as well just be pH. But if I'm just pH, then we already know that correlation is hard for pH. That's the Rosenthal theorem. Okay. So now, in order to prove this, we had to prove a very interesting lemma. So, some of you might know from Andras Ambianis and I a decade ago proposed a conjecture, which came known as the Aa conjecture, which says that basically a quantum algorithm can always be simulated by a classical algorithm on random oracles, right? So, like, given any quantum algorithm that makes a few queries to a random oracle, there is a classical algorithm that makes polynomially more that simulates the quantum algorithm on most oracles. Okay, so we haven't proven that this conjecture yet, but we proved sort of the analogous statement for random sparse oracles. So like for random tables where let's say each row either is completely empty, either is all zeros, or else has a single random one in it. Okay, so for oracles of that kind, we can prove the analog of the Aa conjecture. We can show that if you have got any quantum algorithm and it makes T queries to such an oracle, then that quantum algorithm can be simulated, meaning, we can approximate its probability of accepting by a classical algorithm that makes this number of queries, okay? T to the 5 power, T to the 5th times log T over delta. And the simulation will work on a 1 minus delta fraction of the oracles, okay? So, we actually need this log 1 over delta behavior because we need, to consider when delta is exponentially small, and we want this to still be polynomial, okay? But then, the upshot of this is that having correlation composed with OR, pH to the BQP is no more powerful than just pH itself is. Now, you might be wondering about this exponent of 5, is that tight? I would conjecture that it's not. All I know is that this exponent has to be at least 2, and that's because of Grover's algorithm. Okay, so, this is yet another case where, we face the question, is Grover's algorithm optimal? Or, can you do polynomially better than that? Okay, yeah, and anyway, then we can combine with Rosenthal. All right, I'll just mention one last thing that we can prove and then wrap up. So, we've shown that there is in fact, relative to a random oracle even, PP is not in BQP to the NP. And not only that, not even in QMA to the QMA to the QMA. And so for any constant level of the QMA hierarchy. Okay, and it's in fact not even in MIP star to the MIP star and so forth. And this is amusing because, we learned just a couple of years ago that in the real world, MIP star, which is this multi-prover interactive proofs with entangled provers, is equal to RE, which is recursively enumerable, right? So, it can even solve the halting problem. But that's only in the real world, in the world of no oracle. Okay, in worlds with oracles, with a random oracle, I can even have a stack of, let's say, 100 MIP stars, and fed to each other as oracles, and it still can't even do PP. Okay, so it underscores just how not radically non-relativizing the MIP star breakthrough really was. Okay, so and it contrasts with the situation with like post BPP, let's say, which is relativizingly in BPP to the NP. Okay, so to summarize, relative to suitable oracles, we can almost completely unshackle BQP from the complexity classes around it by exploiting quantum computers' ability to solve the correlation problem. That's fact 1. And fact 2, their inability to beat Grover's algorithm, right? In some sense, these are just the 2 facts about quantum computation that we leveraged over and over. And we can do this even while BPP remains shackled relative to all oracles. Okay, so here are some open problems. Can we get an oracle relative to which P equals NP and yet BQP equals X, right? And is therefore stronger by the time hierarchy theorem. Okay, I think that that's possible, but we weren't able to do it. This is maybe my favorite problem. Can we get an oracle relative to which NP is in BQP, but PH is not in BQP? Okay, I believe that should be possible. In some sense, we made a lot of progress to it, okay, because we proved, oracles where a lot of things happen that have to happen, if this is true, right? Like, like the NP to the BQP outside of BQP to the NP is an example, okay? But, I conjecture that there should even be an oracle relative to which, let's say, BQP contains, the 73rd level of the polynomial hierarchy and does not contain the 74th level, okay? Or for any value of 73 that you want, okay? So, I think that would be a beautiful thing, okay? Is there an oracle where P equals QMA, but they don't equal PP? Again, we ran into technical difficulties when we tried to do that. Is there, an oracle where QMA is not in, BQP to the NP? That seems like related to the famous problem of QMA versus QCMA, quantum versus classical proofs. Then, what are the quantitative limits to, random restriction for quantum algorithms? Okay, now, if you're wondering about the unrelativized world, right, my personal speculations would be, well, that P equals BPP, that is not equal to BQP, that NP is not in BQP. As for is BQP contained in NP in the real world, I am not going to make a bet either way. Well, I'm not going to bet my life on the other ones either, but maybe I would at least bet my car, my house, something. Okay, but there are, it would help a lot if we knew, like, is there any kind of explicit function that instantiates the correlation problem, like without an oracle, analogous to what modular exponentiation does for Shor's period finding problem. I don't know. And can we take things like boson sampling, these sampling-based quantum supremacy experiments, can we make them into decision problems? That's another, huge open problem that would bear on these questions, and that might also have some near-term relevance for quantum computing experiments. All right, so with that, thank you for listening, and I'm happy to take any questions.
Thank you, Scott. Thank you very much for this very nice overview of what's happening in the complexity world on behalf of everybody here. Okay, so we have some time now for questions. Anybody in the audience who wants to ask a question could either raise your hand electronically or just unmute yourself and speak up, whichever you would like. Sorry, somebody? No, okay. So while we are waiting for somebody else to ask a question, let me start off with the question. Yeah, sure. So I wanted to get a feeling for how fragile are these oracle constructions, in the sense of, is it one very carefully crafted relativized world which gives you what you want, or is there a multitude of? So there was one result towards the end that you mentioned, in fact, with respect to a random oracle.
Yes. Yeah. So that, okay. So it's an excellent question, of course. And, and the answer depends on which of our results you're talking about, right? So a few of our results, we show that they hold relative to a random oracle. Okay, so one example is like that PP is not in these hierarchies of the QMA hierarchy, the MIP star hierarchy, right? That's that's even relative to a random oracle. Okay, likewise.
So that's like another refutation of the random oracle hypothesis, because
right. No, and we know that even random oracles, they don't always tell you what is true, in the unrelativized world, right? But once you so I feel like people hope for this totally unreasonable thing, and when it turned out not to be true, and then they said, oh well then then don't use random oracles at all. And I think that's the wrong conclusion. You still want to know what's true, right? But it's just one piece of the story. So likewise, relative to this also we show relative to a random oracle. Okay, that sigma k plus 1 is not in BQP to the sigma k. Okay, but now these were our results that sort of don't depend on Ras-Tal. Okay, anything that depends on Ras-Tal is going to have some part of the oracle that encodes the correlation problem, right? And that, as far as we know today, that makes the oracle rather artificial. And that's exactly why I ended my talk with, one of the things I ended it with was this question, right? If we had an explicit way to instantiate correlation, meaning like, explicit circuits that compute some function, explicit families of circuits that compute functions f and g, where sometimes they're correlated, sometimes they're not, but you can't really tell. It's hard to figure it out classically, right? You need a quantum computer to tell you, right? If we had that kind of explicitization of the correlation problem, then we could actually take many of the oracles that we construct, based on Ras-Tal arguments, and we could turn them into some real world, some more realistic separations. right? So that this is really what it hinges on, I think.
Okay. Yeah. Thanks.
Yeah. Uh-huh.
Yeah. There was a question from Ilya.
Ilya. Yeah. Hi, Ilya.
Sorry, can you hear me? Hi, Scott.
I can hear you. Hi.
Thank you. Thank you for the great talk. As always, I always enjoy listening to your talks.
Thank you.
And I mean, I do have, well, I do have a lot of questions, but I don't want to steal other people's time. But I guess one question finds slightly a different angle, I guess. So
yeah,
we talked about BQP, there's a huge research. But what about, well, somebody who talks about randomness, what about things like EQP, like the exact quantum?
Yeah.
Is it? I know that this is, we had this conversation once, and you told me that it might not be the natural thing. So what do we know about?
It's a very nice question. So Bernstein and Vazirani in '93, when they defined
we've lost your audio.
The exact version. Right,
we lost your audio for the last 10 seconds.
Okay.
Yeah, now we can hear you.
Can you hear me now? All right. So Bernstein and Vazirani, when they defined BQP, bounded error quantum polynomial time, they also defined a class that they called EQP, exact quantum polynomial time, right? Where you have to output the answer with certainty, okay? And then EQP has kind of languished, right, for decades, right? It's hardly been studied, okay? And that's for a couple of reasons. One is that, you know, it's not even a robustly defined class. Like the exact definition of EQP depends on which set of quantum gates you have available to you, right? You have to fix your quantum gate set first, and then, you know, you have EQP like relative to that gate, you know, for that gate set. All right, you know, and then also you could say, look, why do we care about it in practice? Because, you know, quantum computers are always subject to noise, right? Anyway, right? So as long as there's all this, you know, environmental noise, then you might as well allow, you know, algorithmic randomness as well. Okay, but you know, mathematically, you know, one can study this. You know, it's interesting. And so Bernstein and Vazirani, when they gave their algorithm for recursive Fourier sampling, right, that was an exact algorithm. Okay, so that actually implied that there is an oracle relative to which P is not equal to EQP. Okay. Or even, you know, EQP is not in BPP, is not in NP, is not in MN. Okay, all of this follows from Bernstein Vazirani, you know, from recursive Fourier sampling. Okay, but now we could raise as a question: is there an oracle relative to which EQP is not in PH? This question is open. Okay, remains open, okay, because correlation is not going to give you this, right? Correlation, the quantum algorithm inherently involves error, right? It's, you know, it's trying to measure correlation, which cannot be perfect because of the, you know, the sort of Booleanization of F and G, you know, you know, and correlation is currently, you know, or things like it, is currently the only way we know how to get an oracle separation between BQP and PH. Okay, so you know, this would be shown if someone could show that the original recursive Fourier sampling problem is not in PH, right? Then you know, although even then it would only be a polynomial versus quasi-polynomial separation. Right, it would not be polynomial versus exponential. So, you know, if you want polynomial versus exponential of, you know, EQP not in PH, then I don't even have a candidate problem for that. Okay, and so then, you know, everything else that we do on this talk, it would sort of be waiting on that. Okay, so yeah, but I do think this is a nice open problem for someone to solve.
Thank you, and I guess maybe slightly naive question or something you mentioned. Yeah. So we kind of believe, we as a community believe that P equals BPP. Can you share your thoughts about what about?
Sorry, to say it again. That what?
as the community, we believe that you also mentioned that P equals BPP. So I guess your thoughts about could something similar happen with BQP and EQP? Like, is there anything that would collapse BQP to EQP, or it doesn't make sense?
I see. That's an interesting question. Could BQP collapse with EQP? If so, then I think it is not just going to follow from the existence of a pseudo-random generator or anything like that, right? So this is yet another example of the theme I mentioned at the beginning of my talk, right? That with a classical randomized algorithm, you can always play games that involve pulling the randomness out, right? And in the conditional results we have that like P equals BPP if there are good enough pseudo-random generators, right? What all of those involve, of course, is taking a classical randomized algorithm, that takes this randomness string R as an input, and then replacing it with, the output of a pseudo-random generator, right? That takes some small seed, and then, iterating over all the possible values of the seed, estimating its M's acceptance probability under that experiment, okay? And the trouble is there is no analogous thing for BQP algorithms, right? There's no randomness at the beginning that we can now substitute for the output of a pseudo-random generator. Okay, so what that means is that if BQP were equal to EQP, it would have to be for some other reason. Okay, and I'm not even sure what that reason would look like. I can say that there is a sense in which Shor's algorithm can be made exact. You have to be very careful about exactly what you mean and what gate sets are involved, but there's work by Michele Mosca and others that gave an exact version of Shor's algorithm. Okay, but and Shor's algorithm is one of the main examples we know of something you can do in BQP. Okay, but just consider the arbitrary problem of simulating a quantum system, simulating a quantum circuit, right? Like, just because a quantum computer can do that with error, why can a quantum computer do that in an error-free way? Like, I have no idea why, right? Like, if that is possible, it would kind of be shocking to me.
Thank you very much. That was very interesting. Thank you.
Yeah. Mm-hmm.
Yes, so we have time for one last quick question. Anybody? Because I have a question ready if nobody else jumps in.
Oh.
Yeah, so,
okay. Sure.
Yeah, so maybe this will be the last question I wanted to ask. So what would it be significant at all if we had a simulation which had this kind of quasi-polynomial growth? For instance, if we could show that BQP is in classical randomized quasi-polynomial time.
Oh, I mean that would be a breakthrough. That would be that would be like a world-changingly big result, right? It would mean that actually we can, first of all, it would say to all of the chemists and physicists who use supercomputers to try to simulate, quantum mechanical systems, it would say that there is a quasi-polynomial time classical simulation, that will tell you whatever you want to know about your quantum system, right? So it would have practical impact, for them. It would mean that there is only limited reason, to build a quantum computer, right? That there are no exponential speedups that we can hope for from building a quantum computer, but only at most quasi-polynomial speedups. So it would mean that sort of Grover's algorithm maybe would survive, but the kind of speedup that we hope for from Shor's algorithm, that would not survive. Right, so that would be, an enormously world-changing result. But we could even go like less than that. We could say if you could take, a quantum system and a general quantum system involving n qubits, right, and simulate it in 2 to the n over 2 time class instead of in 2 to the n time, right? That's a breakthrough result.
But then, how does it tie in with these complexity classes that we have here, which are not talking about quasi-polynomial time?
Well, I mean, complex, the language of complexity classes is always just like a first rough way to, to phrase the things that we care about, right? And and when like usually it's a very good language, right? Because usually when something is not in some complexity class, then we, it's because it's exponentially hard for that model of computation, right? And now when that approximation breaks down, as it did, for example, for the recursive Fourier sampling problem, where there's, something being not polynomial just meant that it was quasi-polynomial, there I was careful to explicitly note that fact, right?
Yeah, okay, thanks.
Okay, yeah.
So, okay, I don't see any more comments. And in any case, I said that this is the last question. So on this note, let's, on behalf of everybody here, let me thank our speaker, Scott, once again. It was a very nice session. Thank you very much.
All right, well, thank you for inviting me. Great. Okay, so I'll stop the share.
Thank you, Scott. Yeah.
Is this going to be on, like YouTube, or is it going to be archived or something?
Yes.
Okay.
It will be.